Okay, it's exam 4 for spring 2020. First, we start out with a two-lens system. Just treat this like two one-lens systems. So my first one, I have P equals to 30, F equals to 10, and I need to know what Q is, and I need to know what I need to know what Q is, and I need to know what M is. I'll call this M1. So I say 1 over 10 equals 1 over 30 plus 1 over Q. That's 3 over 30 minus 1 over 30. 2 over 30, so Q is equal to 15 centimeters. And then M1 is equal to minus Q over P minus 15 divided by 30, which is negative 1/2. And then we do the second part. So my first image is right about here. It is 15 centimeters from here. Notice I drew it upside down. That's because the magnification is negative. And I also drew it half the original size of the object. It's a little more than half, but it should be half the original size of the object. And now my P value for this distance is going to be 5 centimeters. Because you know this is 20, 20 minus 15 is 5. So I do it all over again. P is equal to 5, F is equal to 2.5. So I say 1 over 2.5 minus 1 over 5 equals 1 over Q. Q is equal then to 5. And then M is negative Q over P, which is negative 5 over 5, which is negative 1. That's M2. And then for the total magnification, I do M1 times M2, or negative 1/2 times negative 1 is equal to 1/2. So my total magnification is 1/2. Which of these aberrations occur in mirrors? One only. In fact, geometric and diffraction aberrations, well, actually those are sort of aberrations, but we haven't talked about them. But chromatic aberrations don't occur in mirrors because chromatic aberrations are due to the index of refraction of the refracting object. And in mirrors, there is no refraction. Which of the following effects is the result of the index of refraction will vary? Which of the following effects is the result of the fact that the index of refraction of glass will vary with the wavelength? Oh, that's what I just said. It's chromatic aberration. Object is placed at a distance of 50 centimeters from a lens. P is equal to 50. The real image forms at a distance of 40 centimeters. So Q is equal to positive 40. It's a real image on the opposite side of the object. So what is the focal length of the lens? Oh, okay, so I just say 1 over F equals 1 over 50 plus 1 over 40. And when I solve that for F, I get 22 centimeters. What is the focal length of a magnifying glass, which remember is a convex lens that produces a magnification of 2 when held 4 centimeters from an object? Okay, so first of all, the magnification is 2, but it's actually negative 2 because a convex lens, no, it's not, I'm sorry, it's positive 2. When you use a convex lens um, as a magnifying glass, then my object would go here inside of the focal point, and my image would go here. So this is my object, that's my image. It is an upright, bigger image. And it's going to be a virtual image too. So M is equal to positive 2, P is equal to 4, and then that's all I really know right now. So I need to know the focal length. I can say 2 is equal to negative Q over P, which is 4. So Q is equal to negative 8 centimeters. And then I'm looking for the focal length, so I say 1 over F equals 1 over 4 minus 1 over 8, so F is equal to 8. If an object is 12 centimeters tall, viewed for the lens with a magnification of 3, what is the height of the image? Well, if it's originally 12 and I magnify it by 3, then the answer is going to be 36. Your makeup shaving mirror, which is a concave mirror, has a focal length of 20 centimeters, it's positive. You stand 40 centimeters from the mirror, what of it is magnification? Well, first of all, if I have Actually, no, I don't know that right off. Never mind. So I'm just going to calculate it. Um, so I have 1 over f, that's 1 over 20, equals 1 over p, that's 1 over 40, plus 1 over q. So q is equal to 40, and m is equal to minus q over p. That's going to be minus 40 over 40, or minus 1. Mirror produces an upright image. The object is 8 centimeters high and to the left of the mirror. That's P. The image is 4 centimeters high. I'm sorry, that's not P. I'm sorry. So this is HO. This is HI. And the center of curvature, which we'll call C, is 8. So first of all, we need to recognize that this image is half the size of the object, and it's an upright image. That means that this has to be a convex mirror. By the way, a convex mirror is going to have a negative focal length. So when I write F, which is going to be C divided by 2, that's going to be 8 divided by 2, or 4. I need to remember that this is going to be a negative 4 because it's a convex mirror. I know that because if I know my ray diagrams, I know that a convex mirror produces images like that. But a concave mirror, if it produces an upright virtual image, this is the object, the image is bigger. Here the object is big and the image is small, but with a concave mirror the image is bigger. Just knowing your ray diagrams will help you with this, so make sure you know those ray diagrams, how to make them. Focal length then is negative 4. The magnification is also positive 1/2 because my image is 1/2 the size of the object. And I want to know what is Q. I also don't know what P is. However, I know that 1/2 is equal to negative Q over P. That's my magnification. And then 1 over negative 4 is equal to 1 over Q plus 1 over P. So what I'm going to do is I'm going to solve this equation where I say P is equal to minus 2Q, and I'll put that in for P. So I get 1 over minus 4 equals 1 over Q plus 1 over minus 2Q. And then I can solve that for Q, and I find that Q is equal to 2 centimeters. Well, that's going to be negative 2 centimeters. It works out to be negative 2 centimeters. Because it's negative 2 centimeters, it's 2 centimeters to the right of the mirror, not to the left. Okay, that's probably the hardest question on the test. You stand 2 meters in front of a mirror that has a center of curvature of 8 meters. The image is big. What is the magnification? Okay, so if I'm standing inside the focal length and my image is big, that means I'm standing next to a concave mirror. Knowing your ray diagrams will help you. That's the only situation where I have that. I'm inside the focal point. And the focal point here is equal to 8 divided by 2. That's 4. It is positive because it's a concave mirror. And I want to know its magnification. P is equal to 2. I need to find Q. So I say 1 over 4 plus 1 over equals 1 over 2 plus 1 over Q. So Q is equal to negative 4, and then M is minus Q over P. That's equal to positive 2. So number 9 is D. I stand 1 meter in front of a flat mirror. What is distance between me and my image? Oh, so I'm right here. This distance is 1 meter. My image, I always look taller in the mirror, is also 1 meter. So this distance is 2 meters. Okay, what type of mirror has produced this image? This has to be a convex convex mirror because the image is smaller and virtual. Convex mirrors only produce smaller virtual images, and concave mirrors do not produce that image at all. Which ray is drawn incorrectly? Let's just look at each one. This one goes parallel. Oh, and then it goes through the center of curvature. That's not right. Which one is that? That's ray number 3. Let's look at the others too. Here I have one that goes through the center of curvature and then back on itself. That one's okay. That was ray 1. And then I have one that goes through the focal point and then parallel to the axis. That one's okay too. But ray number 3 is not correct. Which of these is drawn incorrectly? Here, this one is going through the focal point and then parallel to the axis. That one's okay. This one's going parallel to the axis and then through the center of curvature. Not correct. And then this one goes directly through the center of the lens. So that one's okay. So B is the only one that's not correct. What kind of lens has produced this image? This is going to be a convex lens. Convex lens is the only lens that produces an inverted image. A concave lens will always produce an upright image. So if this is my object, my image would be like right here. That would be my image. It's more like a convex mirror. All right, so convex lens. A convex lens has a focal length of 20 centimeters. Because it's convex, that's positive. The object is located at 10 centimeters to the left of the lens. Which of these describes the image? So let's just draw it out. I have the focal point here. My object is right here. I know, just because I know my ray diagrams, that this object is going to produce an image that is bigger, virtual, and upright. So virtual, upright, and to the right. That's not right because it shouldn't say right. This shouldn't be real, not real. This one shouldn't be inverted. In fact, virtual images are always upright. So C is the right answer. Diffraction gradient has 4,000 lines per centimeter. To find the slit spacing, I just say 1 divided by 4,000, and that gives me 2.5 times 10 to the minus 4 centimeters, or 10 to the minus 6 meters. What is the highest order maximum for wavelength that can be obtained with a gradient with 600 lines per millimeter? So first of all, I have to find D. That's 1 over 600. 1.6 times 10 to the minus 3 millimeters, or 1.6 times 10 to the minus 6 meters. Be careful with your metric system, okay? And then I say d sine theta equals m lambda. D is 1.6 times 10 to the minus 6. Sine of 90 equals m times lambda, 450. And then I solve that for m. And m works out to be, well, I don't know, it's some value over 3. It's like 3 point something. I don't know what the something is. But when you're finding the order number, you can't have a fraction of an order. So you always round down. Even if it was 3.9, it would still be 3 would be the answer. That's the highest order maximum. Double slit looks like this. If you place a screen over here, what are you going to find? Well, you're going to see a bright spot, followed by a dark spot, and a bright spot, and a dark spot, alternating. You don't see two spots, you see alternating dark and bright bands of light. Okay, number 19 takes a little bit. So first we need to find, we have a situation like this. And I want to know how far is the second bright fringe from the central dark maximum. What is this distance, y? Okay, so I know that this is a triangle, and I can find this angle theta. So that's the first thing I need to do, is find the angle theta. So I say d sine theta equals m times lambda. And if I solve that for theta, m is equal to 2, lambda is 650 nanometers, over d, which is 0.2 times 10 to the minus 3 I get 0.0065. Right? Oh no, I have to do the inverse sign of it. I get 0.3724. So let me fix something. This is actually the inverse sign of this quantity. And that gives me 0.3724 degrees. And then if I want to find y is equal to L tan theta, where L is this distance right here, which is given, that's 5 meters. So 5 tan of 0.3724. I get 100. Oh, no, I have a mistake here. I'll find it. I'm going to pause. Okay, there was no mistake, but the answer here is 3.3. So it's 3.3 times 10 to the minus 2 meters, or 3.3 centimeters. Okay, in Young's double-slit interference apparatus, by what factor is the distance changed when the slit separation is doubled? So d sine theta equals m lambda. And I'm doubling the slit separation. If I double that, what happens to the distance between them? Well, if that doubles, this has to halve. And if that halves, the angle halves, then that means that this also halves. So the distance between the light and dark fringes will halve if you double the slit separation, which, you know, it's not really intuitive. If I put those slits farther apart, then the fringes move closer together by the same amount. Interference, what type of interference is this? That's destructive, because the peaks and the troughs line up. By what amount are these out of phase? For number 22, that's going to be, these are 180 degrees out of phase. When they're completely out of phase, that's 180. Two waves of wavelength 4 meters travel through space. The first wave travels 8 meters, the second wave travels 10 meters. So that means that they are, the path length difference is equal to 10 minus 8, or 2 meters, and that's equal to a 1/2 wavelength. So when I'm offset by a half a wavelength, that's when I get total destructive interference. Look, these guys right here, they're offset by a half a wavelength too. So this is a half wavelength at 180 degrees out of phase, and so I get total destructive interference. This type of interference is a light incident on a circular object. Here I want to know what is the slit width for this green light of gaseous mercury. Say A sine theta equals m lambda. So A is what I'm looking for. M is 4. 546 is lambda. All right, what must the path length difference be for this? It's going to be 1 wavelength. This would be a half a wavelength. This would be 1, this would be 2, this would be 3, 4, half, 3 halves, 5 halves, 7 halves, and on and on. Single slit is used to create an interference pattern. If you increase the width, what happens to the width of the central bright fringe? It's going to be narrower. A sine theta equals m lambda. If this goes up, this goes down, and that theta is what defines the size of the central bright fringe. And then, of course, I really miss all of you. Look forward to seeing you. You won't be in my class next semester, but nonetheless, you can drop by and see me. Have a great day.